In today's video, we're going to be talking about sound properties. So after watching this video, you should be able to know the correlation between pitch and frequency, know how sound intensity is measured, and understand how beats are created. Let's get right to it. The first thing I'm going to talk about is frequency, which is something we've hit on before. Frequency is basically how often the particles of a medium vibrates when a wave passes through the medium. So how often is that vibration occurring? And the unit to measure frequency is the hertz, which is abbreviated by Hz. And 1 hertz would equal 1 vibration per second. So it's based off of a vibration per how many seconds. The pitch is a property of sound, and basically what that relates to is the frequency. So a high pitch will correspond to a high frequency. So if you have a sound of 200 hertz compared to a sound of 100 hertz, your ears will perceive the 200 hertz sound as a higher pitch than the 100 hertz sound. And I don't know if you guys have ever listened to like a dog whistle. Well, you really can't listen to a dog whistle, but basically dogs are able to hear much higher pitched sounds or higher frequency sounds than, say, the human ear is. And I know there's apps on phones and ringtones on phones that you can get to have a really high pitched sound that supposedly older people can't hear. I don't know how true that is because I haven't really tested it out, but kind of interesting to think about. The intensity of a sound wave is basically measuring the amount of energy that is transported past a given area of the medium per unit of time. And that's the intensity of the sound wave, and that is going to be called the decibel scale. And so typically it's shown as dB, the decibel scale, and it's based on multiples of 10. And you may ask yourself, well, what is the loudness of a sound wave based upon? Well, it's based upon the amount of energy or the amplitude of the wave. So if a wave has a really high energy or a lot of energy or a high amplitude, I should say, then it would have a higher decibel scale or dB, and it'd have much more intense sound. Okay, so when you yell, you're actually releasing more energy than, say, when you whisper. Okay, so that's how sound waves are measured, is on this decibel scale. So here's an example. A periodic wave is produced by a vibrating tuning fork. The amplitude of the wave would be greater if the tuning fork were struck more softly, struck harder, replaced by a lower frequency tuning fork, or replaced by a higher frequency tuning fork. Well, if you want to increase the amplitude of a wave, you need more energy. So how are you going to get more energy into that tuning fork? You're going to have to strike it harder. Okay? And the harder you strike it, the louder it will sound. Okay, and basically what you're doing is you're producing more energy by doing that. Here's another example. Increasing the amplitude of a sound wave produces a sound with lower speed, higher pitch, shorter wavelength, or greater loudness. Well, amplitude is directly related to the volume, if you will, of a sound. And so increasing the amplitude will create greater loudness, or make it appear, not really appear, but actually be louder, because it has more energy, and that energy your ears perceive as loudness. Speaking of loudness, this is just kind of give you some idea on how many decibels decibels things are that you may see in daily life. So if you listen to raindrops, say, outside, that's about 40 decibels. Okay? A normal conversation is about 60 decibels. If you go to a rock concert, it's about 105 decibels. I don't know if you guys have ever gone to one of those, but sometimes your ears will actually be ringing after a rock concert. And that's because you're kind of getting into that point where it's getting dangerous to be listening to such loud sounds. Here's one that's kind of interesting for those of you who listen to music on an iPod. At peak volume, you're getting in your ears 115 decibels, and it's certainly a concern for this generation that we're going to have a lot of people who have hearing issues as they get older, because this is the age of listening to music and having earbuds in your ear, and it actually can damage your hearing. The loudest thing here is like gunshots or fireworks, 140 decibels. If I'm not mistaken, the Guinness World Record was set in Seattle, the stadium in Seattle. I forget the name off the top of my head, but basically the crowd was able to produce about a sound of about 140 decibels with them all screaming and that type of thing. It's the loudest stadium, I believe, in the United States. So kind of cool to think about. Just like what we had talked about in the previous unit, sound waves can undergo constructive and destructive interference. Sound is a pressure wave, so it's a longitudinal wave, and it consists of compressions and refractions. And if you need a refresher on what that is, check out the previous lesson because we talk about it there. Constructive interference occurs when two compressions or two refractions meet up. Okay, and when they meet up, you have constructive interference. Destructive interference occurs when you have compression waves meet up with a refraction wave. So you have to have two different types. A compression wave with a refraction wave will create destructive interference, whereas constructive interference can occur with either two refractions or two compressions. It doesn't really matter which one you want to go with. That's constructive interference, because you're going to build that wave up with two of a kind, whereas destructive interference causes the wave to get destroyed because you have one of one type and another of another type. Now, what are beats? Basically, when you have two sound waves of similar but not exactly the same frequency happening at the same time and they approach your ear, they interfere with each other to create an alternating loud and then quiet sound, and it sounds like a beat. This result of alternating constructive and destructive interference is what a beat actually is. So it's something, two sound waves that have very similar frequencies but not quite the same, and it causes for constructive and destructive interference. And a picture's worth 1,000 words. This top wave up here, this is 4 hertz. Okay, and this wave down here is 5 hertz. So they're very close, right, in terms of their frequency. When you kind of take these two waves and put them together, this is what you get. You get areas of constructive and destructive interference going on here, and it appears to produce beats, is what you hear. Okay? And you may say, well, how is this relevant to anything in daily life? Well, I will tell you in just a second with dealing with like musical instruments and how beats can be useful. There is a formula to figure out the beat frequency, and basically the frequency of beats, which is what this is, the frequency of beats equals whatever your one frequency is minus your other frequency, and this will always be a positive number. You can't have negative frequency. Okay, so make sure you put your absolutes in there. So how can this be useful? Well, keep this formula in mind, because I'm going to have an example problem in about 2 slides, and we're going to be using that. The beating phenomenon, or these beats that are created from two waves that have similar frequency, can be used to help tune instruments such as like a guitar. So let's say you play a note on, say, one of your strings on your guitar, and you play try to play the same note on a different string, and you listen and you hear a beat. It means they're not in tune with one another, or they're not hitting the same note. And so if you hear beats, basically the tension in one string needs to be adjusted to minimize that beat frequency. And when you don't hear any beats at all, you now know your guitar strings are in tune with one another. All right, let's take a look at an example problem. This might make a little bit more sense. While tuning her guitar, Sandra plays an A note on the 5th string at exactly 110 hertz. Sandra then plays on her 6th string the same exact note, or tries to produce the same tone. However, when she plays on the 6th string, she hears a beat pattern. So right now we know that it's not in tune because we're hearing two different frequencies. Where the loudest amplitude, however, when she frets and plays the 6th string, she hears a beat pattern where she hears the loudest amplitude 2 times each second. Assuming the fifth string is perfectly in tune, which of the following could be the frequency of the out of tune sixth string? Choose all that apply. So our choices are 108 hertz, 109.5 hertz, 110.5 hertz, or 112 hertz. Well, we know 110 hertz is in tune, and we're hearing a amplitude or a beat basically 2 times each second. Okay, so that means that we have a frequency of 2 hertz. Okay, so you're hearing it 2 times each second. So basically, what it means is Sandra's sixth string must either be 2 above 110 hertz or 2 below 110 hertz. So 110 plus 2 would equal 112 hertz. Okay, that's going to be one possibility, and that would be D. Or we can take 110 minus 2, and that would be equal 108 hertz, and that would be A. All right. So basically, those would be our choices, either A or B. I'm sorry, A or D. B and C are not possibilities. All right, that takes care of this video. I will see you guys next time.